Right now, as of March 2026, AI models in China are burning through 140 trillion tokens every single day. That is not a cloud usage statistic. That is not a software metric. That is a localized stress test on the physical power grid of the Earth. Welcome to the Deep Dive. If you are a data scientist, a machine learning engineer, or a tech professional navigating the bleeding edge of artificial intelligence, you know exactly how overwhelming the weekly paper drop can be. You're constantly building, deploying, and optimizing, which means you need the signal, not the noise. That is our mission today. We are unpacking a massive stack of tech reports, academic papers, and industry blogs from this week in July 2026. We are going straight into the mechanics of four crucial pillars of modern AI: hardware economics, inference optimization, multi-agent orchestrator dynamics, and generative physical AI. We have an immense amount of ground to cover, and you're going to see exactly how all of these layers crash into each other.
It is a fascinating collision, really, because what we are witnessing right now is a fundamental structural shift in the industry. For the past 4 years, the entire AI conversation has been intensely software-centric. We talked about parameter counts, we talked about training data sets.
We completely obsessed over benchmarking scores on things like MMLU or human evil.
Exactly, yeah. But the barrier between software, meaning the weights and the models themselves, and physical reality, meaning the actual silicon, the energy grids, the copper wire, and the robots, is rapidly collapsing.
It is hitting a wall.
You simply cannot scale software infinitely without violently slamming into the hard limits of the physical world.
Okay, let's unpack this and look right at that physical limit.
Yeah.
The sheer scale of the token economy.
Yeah.
According to a report this week from the South China Morning Post, they were covering a recent industry conference, and daily AI token consumption in China surged 1,000-fold in just over 2 years.
It is staggering.
Putting that 140 trillion mark daily. When I read that number, my mind immediately went to the physical infrastructure required just to move that much data through memory buses.
You really have to fundamentally shift how you visualize these numbers. In the current ecosystem, tokens equal compute, and compute equals energy and hardware.
Right.
When you are processing 140 trillion tokens daily, you are drawing a quantifiable, massive amount of electricity from the grid.
And creating a ton of heat.
Oh, massive amounts of heat in data centers, which, requires even more energy to cool. Every single token generated requires matrix multiplications.
Yeah.
Every multiplication requires loading weights from high bandwidth memory into the compute cores. And moving data across a chip costs exponentially more energy than the math itself.
So the token economy is no longer just a digital economy.
No, not at all. It is a heavy industrial economy now.
Which perfectly sets up the first major development in our stack today. We are seeing top Chinese AI labs, specifically DeepSeek and Zhipu AI, fundamentally altering their strategies.
Right, they're taking a totally different path.
They are no longer just building models, they are self-developing custom inference chips.
Yeah, joining the ranks of companies like OpenAI who have been moving in this exact direction.
But let me stop here for a second, because designing custom silicon, application-specific integrated circuits, or ASICs, is notoriously risky.
Oh, incredibly risky. The graveyard of hardware startups is vast.
Exactly. So why are software labs taking on the massive capital expenditure of chip fabrication instead of just renting GPUs from the established players?
Because the end game for foundation models has changed, from just raw capability to pure unit economics.
It is all about the margins.
Right. When you rely on generalized GPUs, you are paying a massive premium for flexibility.
Because they have to do everything.
Exactly. A generalized GPU is designed to do a lot of different things very well. It has silicon dedicated to rendering graphics. It has varying levels of precision support. It is built to train diverse neural network architectures.
But if you are DeepSeek,
right. If you are DeepSeek and your daily token throughput is in the hundreds of billions or trillions, you do not need flexibility. You need absolute ruthless efficiency for your highly specific proprietary workload.
So they are cutting out the generalized bloat on the chip itself.
Precisely. Custom silicon allows for hardware optimization that is physically tailored to highly specific algorithmic architectures.
Like their MoE models?
Exactly. Take the DeepSeek R1 architecture, for instance. It relies on very specific routing mechanisms and memory access patterns that are unique to how they handle sparse activation.
And a normal GPU struggles with that.
Yeah, on a generalized GPU, those memory access patterns might cause bottlenecks, forcing the compute cores to just sit idle while waiting for data from memory.
The classic von Neumann bottleneck.
Right. But if you design your own chip, you can hard-code the physical silicon pathways to perfectly match the mathematical pathways of your algorithm.
Wow.
You can increase the SRAM close to the compute cores exactly where your model needs it.
So the efficiency gains are huge.
You achieve throughput and energy efficiency that a generalized GPU simply cannot physically match. It is vertical integration driven entirely by survival economics.
You are aggressively cutting operational costs at scale.
And simultaneously reducing your dependency on third-party hardware supply chains.
And when you start talking about operational costs at the scale of national token consumption, you inevitably run into macro geopolitics.
You really do.
We have to look at the broader global stage here. There is an opinion piece in the South China Morning Post that makes a very specific structural claim about the U.S.-China AI competition.
Yeah, this was an interesting angle.
Now, we are reporting this impartially, strictly looking at the economic mechanics the author presents.
Yeah.
The premise is that the AI race is no longer an algorithmic war.
Right.
It is boiling down to a physical contest over electricity and power grids.
Which makes a lot of sense when you look at the energy draw.
The argument is that as AI models inevitably become highly capable commodities, the true bottleneck, and therefore the strategic advantage, is entirely about electricity output and the resulting service pricing.
It is a highly compelling macroeconomic lens to apply to our field. I mean, think about it from a purely industrial perspective.
Right.
If you assume a near future where foundational models from different labs reach a functional level of parity,
Where they are essentially commoditized intelligence utility.
right, then the differentiator for any enterprise using that intelligence is just the cost of inference.
Because the models are all basically as smart as each other.
Exactly. And the cost of inference is primarily dictated by the amortization of the hardware and the ongoing cost of electricity to power and cool it.
So the power grid becomes the moat.
The source argues that the nation with the most robust, scalable, and cost-effective power grid will dictate the global pricing floor for AI services.
That shifts the entire battlefield.
It really does. It is no longer just about who has the best researchers. It is about who has the most efficient baseload power generation, the best nuclear or renewable integrations, and the most resilient transmission infrastructure.
It is the ultimate reality check for software engineers.
Yeah. You cannot code your way out of the laws of thermodynamics.
But that doesn't mean we aren't trying to engineer our way around these physical constraints. Which brings us to how model architecture is adapting to the hardware reality. Let's look at Tencent's new Hunyuan Hy3 model.
This is a great example.
This is a massive 295 billion parameter model.
Huge.
But the critical optimization here is that it only uses 21 billion active parameters during inference.
Right, a massive reduction.
Despite dropping roughly 93% of its active compute per token, it is achieving a 90% agent task resolution rate, surpassing models like DeepSeek V4 Pro and Qwen 3.7 Max on key benchmarks.
Yeah, and they are doing this through a highly optimized mixture of experts, or MOE architecture.
Exactly. Mixture of experts is the software layer's direct response to the hardware and energy constraints we just outlined.
Right. You get the reasoning capability and the vast world knowledge of a 295 billion parameter dense model, but without the devastating computational penalty of running a massive forward pass through every single parameter for every single query.
I was thinking about this architecture earlier, trying to visualize what's actually happening at the compute layer for any undergrads listening.
It can be tricky to wrap your head around at first.
And it reminds me of a massive world-class university research hospital.
Oh, I like that analogy.
Imagine that entire hospital complex represents the total 295 billion parameters.
Okay.
Now, if you walk into the emergency room with a sprained ankle, you do not ask the chief of neurosurgery, the head of oncology, and every single resident in the building to examine your ankle.
Right. That would be an astronomical waste of institutional resources.
Exactly. Instead, you walk in and you meet a highly trained triage nurse.
And in the MOE architecture, this is your routing network.
Yes, the router. That router looks at your specific problem, which is the input token, and sends you only to the specific specialist, the expert network that handles orthopedics.
So you get the benefit, the backing, and the knowledge of this massive institution.
But you only pay the cost, or in our case, the compute and energy, of consulting a few specific experts.
Right. The 21 billion active parameters are the specific doctors treating your query, while the rest of the massive model just sits idle in memory, saving precious power.
That is exactly how it functions. But the true engineering challenge of MOE, the reason it is so difficult to get right at scale, is building that triage nurse.
The routing algorithm.
It has to make the correct decision instantaneously for every single token across hundreds of layers.
And it is not just about accuracy. I mean, it is about load balancing.
Right, because if you have a hospital where the triage nurse sends 90% of the patients to one single doctor,
That doctor's total overwhelmed, the queue backs up, and the rest of the hospital is wasting space.
in hardware terms, if your router sends all the tokens to one expert, you get massive compute bottlenecks on specific GPUs while other GPUs sit idle.
Which just completely destroys your inference speed.
Exactly. So when Tencent achieves a 90% agent task resolution rate with only 21 billion active parameters out of 295 billion, it tells us that their routing algorithm and their specific expert subnetworks are astonishingly well-balanced.
They're achieving frontier-level reasoning while actively minimizing the physical electricity draw required to generate the output.
So building custom silicon and migrating to MOE architectures are the structural ways to manage costs.
If we connect this to the bigger picture, you optimize the physical chip and you optimize the mathematical model.
But the layer in between those two, the inference engine actually translating the model to the metal, has to be utterly flawless.
It has to be. I mean, you can fabricate the greatest custom ASIC in the world, and you can design the most elegant MOE model, but if the software framework handling the memory allocation and the batch scheduling is inefficient, you are still leaving massive amounts of compute on the table.
Which takes us straight into inference optimization. We are talking about squeezing every last drop of performance out of your system.
Right.
Let's dig into the latest updates from the LMSYS blog regarding the SGLang framework, specifically a new feature called DSpark.
This is a really clever piece of engineering.
This deals with speculative decoding, using confidence-driven variable length verification.
Yeah.
Let's establish the baseline of speculative decoding first, because it is brilliant.
It really is a game changer for latency.
Normally, autoregressive generation is entirely memory bandwidth bound. You load massive weights into the GPU's memory just to generate one single word.
And then you do it all over again.
It is brutally slow. Speculative decoding acts like the predictive text on your phone, or like when you're talking to a close friend and you know exactly what they're going to say, so you try to finish their sentence.
Right, you're guessing ahead.
Instead of the massive, slow AI model generating one word at a time, you use a tiny, lightning-fast draft model to hallucinate the next 5 words instantly.
And then the massive smart model does one single forward pass to read all 5 words at once and basically check the work.
Because GPUs love parallel processing.
They do. If the tiny model guessed correctly, the large model approves the whole batch in one shot, and you just bypassed massive memory latency.
It is one of the most elegant solutions we have for inference speed.
It is, because checking a sequence of tokens in parallel heavily utilizes the tensor cores, making it compute-bound rather than memory-bound, which is exactly where GPUs excel.
But as anyone who has tried to deploy speculative decoding in a high-traffic production environment knows, it has a glaring vulnerability when you scale it up.
Oh yeah, and this is precisely what DSpark solves.
Right, because DSpark introduces variable length verification. Why does that specific change matter so much to the architecture?
It all comes down to the realities of batch sizes and the KV cache.
Okay, break that down.
Well, when you are serving a frontier model in production, you are not just answering one user's prompt. You are processing hundreds or thousands of sequences simultaneously.
That is your batch size.
Right. Speculative decoding trades extra compute cycles in the draft model for fewer total decode steps in the target model.
Makes sense.
But think about the memory overhead. If your system is under heavy load, verifying a fixed length of guessed tokens, say, strictly forcing the big model to verify exactly 5 tokens every single time for every single sequence in a massive batch becomes a crippling bottleneck.
Because if the draft model is wildly guessing wrong, the big model is wasting FLPs grading terrible homework.
Exactly. And worse, it is wasting VRAM.
Right.
Every guessed token has to be written to the KV cache, which is the memory structure that stores the keys and values of previous tokens so they don't have to be recomputed.
And memory is precious.
Very. If the draft model guesses 5 tokens and the target model rejects the last 4 because the first guess was wrong, you have to flush those rejected tokens out of the KV cache.
Oh, wow. It sounds expensive.
It is. When you multiply that memory churn across a massive batch size, the target model gets completely bogged down.
So how does DSpark fix this?
DSpark solves this by making the guess length dynamic based on mathematical confidence.
Okay.
If the draft model's probability distribution for the next token is highly confident, DSpark lets it run and guess 7 or 8 words.
Just lets it cook.
Yeah. But if the draft model's probability distribution is flat, meaning it is uncertain, DSpark immediately cuts it off after 1 or 2 words.
That is incredibly elegant. You're actively pruning the computation tree before it even grows.
Exactly. By dynamically adjusting the guess length based on real-time confidence scores, DSpark prevents the verification step from choking the main model.
It keeps the KV cache clean.
And keeps the entire system highly efficient, even under massive, highly concurrent batch loads.
Now, let's pivot from inference optimization to training, specifically reinforcement learning post-training.
Okay, yeah.
We have significant news about the Miles-RL framework. They are bringing DeepSeek V4 FlashRL training natively to AMD Instinct MI355X GPUs using the ROCm software stack.
This is a huge deal.
Now, hold on. ROCm has been a pain point for ML engineers for years.
It definitely has a reputation, yeah.
We hear so much about the absolute ubiquity of NVIDIA's UDA ecosystem. Is it actually viable that a major framework like Miles is providing day zero support for large-scale MOE reinforcement learning post-training on AMD hardware?
It is not just viable. It is a critical maturity milestone for the industry.
Really?
Yeah. Going back to our first topic, the industry desperately needs hardware diversity to maintain competitive pricing and break vendor lock-in for data centers.
Because NVIDIA basically sets the prices right now.
Right. But from a purely technical standpoint, this is a massive achievement. Modern foundation models are no longer just pre-trained on mountains of tech.
The frontier capability comes heavily from reinforcement learning post-training.
Yes. And agentic RL requires a pipeline we call Tita-to in token out.
Because an agentic rollout is not just a single static generation, it is highly iterative.
Exactly. It is a highly volatile, complex chain of events. The model makes a generation call, it uses an external tool, it receives a response from the environment, it updates its context, and it resumes generation.
It is doing a lot of back and forth.
To run this efficiently at a massive scale requires incredibly tight, low-latency integration between the inference engine, which is doing the rollout generation.
In this case, utilizing things like SGLang.
Right, and the training engine, which is calculating the loss and updating the weights, like Megatron.
So you are constantly rapidly switching between generating text and backpropagating errors.
And you are doing this across hundreds of GPUs simultaneously.
Wow, so you have inference weights and training weights co-residing and interacting in the same memory space.
Exactly. It is a memory management nightmare.
I can imagine.
Doing this efficiently on NVIDIA hardware with CD is already a profound engineering challenge.
Right.
Achieving day zero support for this level of complex, memory-intensive hybrid pipeline on AMD hardware via their ROCm stack proves that the open-source software ecosystem has finally matured.
It has matured to the point where it can effectively abstract away the hardware layer.
Exactly. It proves that the compiler and the primitive libraries in ROCm can handle the most complex post-training pipelines without requiring a massive translation layer that kills performance.
Which gives data center operators massive leverage.
Because they can now deploy cutting-edge RL on non-NVIDIA silicon seamlessly.
So what does this all mean? Let's pull these threads together.
Yeah.
We have the foundational hardware being aggressively optimized with custom ASICs. We have highly efficient MOE architectures slashing active parameters. And we have the inference engines squeezing out every drop of performance using dynamic speculative decoding.
It is a massive stack of optimization.
The result of all this optimized infrastructure is that we now have the computational capability to run complex, multi-step autonomous agentic systems persistently.
Right. We can actually afford to run them.
But what happens when those multi-agent systems break down?
Oh, they definitely break down.
Because if you have built one, you know they do. And debugging a system of interacting black boxes is an absolute nightmare.
It is the crux of the current reliability bottleneck.
Right.
As we move from simple single-turn chatbots to complex autonomous agents executing multi-step workflows, a failure is no longer just a weird, hallucinated response on a screen.
No, a failure is a broken corporate process.
Or a failed financial transaction or a corrupted database. The stakes for reliability have shifted exponentially.
Which brings us to the actual dynamics of these multi-agent systems. There is a fascinating paper accepted to ICML 2026 from Nanjing University, covered this week in Pandaily.
This paper is brilliant.
It really is. This paper tackles a massive headache for any data scientist working in this space.
Yeah.
Why do complex multi-agent systems catastrophically fail even when the individual models inside them are highly capable?
It is one of the most critical questions in AI deployment right now.
Yeah.
You can take 3 state-of-the-art models, assign them distinct, well-defined roles, say a researcher agent, a coder agent, and a reviewer agent, and put them in a collaborative loop.
And individually, isolated in their own environments, they pass every benchmark with flying colors.
Right. But together in a dynamic loop, they suddenly get stuck in infinite logic loops. They hallucinate shared realities that don't exist, or they completely lose the context of the original overarching goal.
It is so frustrating to watch happen.
It is. The Nanjing University paper presents a mathematically rigorous breakthrough, though. They prove that the core of these failures does not originate from the individual execution agents.
The degradation stems entirely from the orchestrator.
Exactly.
Let's visualize what orchestrator entropy dynamics actually means in practice.
Okay.
Think of a multi-agent system exactly like a symphony orchestra.
I love this analogy.
The individual agents are your musicians. The violinists, the cellists, the percussionists. They're world-class.
Right.
They know how to play their instruments flawlessly. But the orchestrator agent is the conductor.
Yeah.
If the conductor starts giving erratic, chaotic, and mathematically unpredictable signals, if their tempo is violently shifting and they are cueing the brass section when the string should be playing a solo, the resulting music will be a total disaster.
It absolutely does not matter how brilliant the violinists are.
Exactly. In information theory, that chaos and unpredictability in a system state is measured as entropy.
Yes.
The researchers prove that we can predict and diagnose system degradation by mathematically measuring the Shannon entropy of the orchestrator's commands and routing decisions over time.
The symphony analogy is spot on because it highlights the cascading nature of the failure.
How so?
Well, high entropy in the orchestrator state mathematically signifies that it has lost the deterministic thread of the overarching goal.
It is confused.
Right. Its probability distribution for the next logical step has flattened out, so it is essentially guessing.
And what happens then?
Consequently, it starts sending randomized, incomplete, or conflicting context windows down to the subagents.
And the execution agents then react perfectly to the terrible instructions they receive.
Exactly, which compounds the error and feeds corrupted state data back up to the orchestrator, creating a death spiral.
Wait, if the orchestrator is the single point of failure, does this mean the industry has been spending way too much time fine-tuning individual models on coding benchmarks and completely neglecting the engineering of the management layer of these systems?
The data absolutely validates that exact concern.
Really?
Yeah, we have over-optimized the workers and completely neglected the manager. What's fascinating here is that achieving trust and reliability in multi-agent systems requires us to fundamentally shift our entire paradigm of interpretability.
Right, because we can't just look at the weights anymore.
Exactly. Historically, interpretability was about mechanistic analysis, looking inside a single neural network, trying to figure out which specific attention heads activated for a specific concept.
But in a multi-agent framework, the system is a dynamic network of interacting black boxes.
You cannot mechanistically interpret a conversation.
So what do we do?
Therefore, we must monitor the entropy dynamics of the orchestrator as a continuous live health metric.
So you are basically tracking the variance in the orchestrator's semantic output.
Exactly. By analyzing the mathematical variance in the messages and the API calls the orchestrator makes over a temporal window, we can detect the exact moment the system begins diverging from its objective.
Oh, wow.
If the entropy spikes, you halt the system instantly before those cascading failures reach the execution layer and affect the real world.
It is a profound shift from analyzing static model weights to analyzing dynamic communication protocols.
This raises an important question, though. If we are currently having to develop advanced information theory mathematics just to reliably orchestrate agents in a text-based, highly controlled, perfectly sterile digital environment,
Right.
how on earth do we orchestrate them when they have to interact with the messy, chaotic, unpredictable physical world?
That is the ultimate frontier. And it is exactly why the physical and software worlds are colliding right now.
The physical world does not have a clean, predictable ATI.
No, it has friction, it has latency, it has wind, it has gravity, and it has absolute unmitigated chaos.
Which perfectly brings us to our final pillar today, generative physical AI and embodied robotics.
Let's dive in. To have an AI interact with the real world safely, you first have to be able to simulate the real world with extreme fidelity.
You have to build the sandbox first.
Exactly. Let's look at Microsoft's Aurora 1.5 Earth System model. This is a massive structural update to atmospheric modeling.
It is incredibly detailed.
It adds 22 new atmospheric and physical variables. We are talking things like specific humidity, wind vectors at multiple geopotential heights.
And the resolution is incredible.
Yeah, it achieves hourly temporal resolution, and critically, it introduces probabilistic ensemble forecasting.
If we connect this back to the very beginning of our deep dive, you realize immediately that this is not just about an AI application telling you if you need to carry an umbrella tomorrow.
No, this is enterprise level.
This is about critical, real-world energy applications at a national scale.
Like the power grids we were talking about.
Exactly. High-fidelity physical simulation is absolutely mathematically necessary to predict localized power grid loads and renewable energy generation.
Because the load changes based on the physical environment.
Right. When you are managing the fragile energy infrastructure required to support the massive 140 trillion token economy we discussed, you need to know exactly how a localized cloud cover event will impact your solar yields.
Or how a sudden 2-degree temperature drop will spike heating demand across a city hour by hour.
Because the grid has to be perfectly balanced in real time.
You cannot store massive amounts of AC power. Generation must perfectly match load.
Exactly. And probabilistic ensemble forecasting means Aurora 1.5 isn't just giving one deterministic guess.
It's running multiple scenarios.
It is running dozens of simulations with slightly perturbed initial conditions to generate a highly accurate probability distribution of the weather.
Which ties directly into that geopolitical AI electricity contest.
You simply cannot optimize a national power grid for AI baseloads without accurately simulating the Earth's physics.
And simulating the physical world also means generating its visual and audio components natively.
Yeah, the sensory inputs.
We briefly saw Meta detail their Muse image and video models this week.
Those were impressive.
We are talking about extremely high visual fidelity, highly precise spatial temporal editing capabilities, and native audio support.
Right, giving AI the foundational ability to generate and manipulate complex multimedia environments natively.
Inherently understanding the physics of light, motion, and sound without external rendering engines.
But the real convergence, the moment all of this technology truly hits the real world, happens when we put these capabilities into physical bodies.
Yes, let's talk about embodied AI and robotics, specifically focusing on the open source LiRobot and Lingbot ecosystems.
The robotic space is moving at an astonishing pace right now.
It really is.
LiRobot, fueled by the intense collaboration between NVIDIA and Hugging Face, is rapidly cementing itself as the de facto open robotics community standard.
But the specific architecture of how these robots actually think is detailed in the Lingbot papers trending this week.
Let's do a deep dive into the Lingbot stack.
Because it breaks down the entire problem into discrete, highly complex models. First, you have Lingbot Video,
Right.
which utilizes a mixture of experts' architecture specifically for embodied intelligence pre-training, basically learning physics from video data.
Yeah.
Then you have Lingbot Map, which is a 3D foundation model that handles real-time streaming reconstruction of its physical environment at 20 frames per second.
That is massive throughput for a local model.
And finally, you have Lingbot VLA 2.0, which stands for Vision Language Action, essentially the brain making the decisions.
Yeah.
Now, I have to push back on the reality of this stack.
Okay, go ahead.
We are taking models that can predict global atmospheric pressure and generate photorealistic video, and we are trying to cram those massive compute-heavy brains into physical robots using VLA models.
Right.
Are you telling me we have actually solved the hardware bottlenecks fast enough to support battery-powered robots that need to process real-time 20 frames per second 3D environmental streams natively?
It is an entirely valid skepticism, and the answer to your question is exactly why every single topic we have discussed today is intricately interconnected.
Okay, hit me.
The reality is no, you cannot put an off-the-shelf, massive, dense language model onto a generic GPU inside a robot and expect it to navigate a complex room.
The memory latency would be fatal. The robot would freeze while calculating its next step and crash into a wall.
Exactly. But think about the specific technological stack we just built from the ground up today.
We are essentially building the ultimate edge computing device.
Exactly. You cannot put an advanced AI into a physical robot without custom inference chips, like the A6 DeepSeek is building.
Because they are physically optimized for extreme low-power, high-throughput specific tasks, rather than generalized rendering.
Right. And you cannot run the onboard reasoning without highly optimized memory management and speculative decoding like SGLang's DSpark dynamically managing the KV cache.
To ensure the robot processes visual tokens fast enough to react to a dynamic environment without running out of VRAM.
Exactly. You cannot process 20 frames per second of 3D spatial data without MOE architectures heavily dropping inactive parameters to save battery life.
Just like the Hunyuan model.
Right. And finally, you absolutely cannot have that robot execute a complex, multi-step physical task like repairing a sensitive component or navigating a hazardous environment without a highly reliable orchestrator.
That is constantly mathematically monitored for entropy dynamics.
Yes, ensuring the robot doesn't get stuck in a logic loop and perform a dangerous action repeatedly.
It all clicks together.
The deep software optimizations, the multi-agent mathematics, and the custom physical silicon are the only way embodied AI becomes physically viable in the real world.
It is genuinely incredible to see how the entire stack, from the macroscopic power grid down to the microscopic silicon pathways, relies on every single layer operating at maximum ruthless efficiency.
It is a dense, highly interconnected web of engineering.
Let's briefly recap the massive ground we covered today.
Yeah, we covered a lot.
We started at the macro level, looking at the brute force economics of custom chips, the US-China power grid contest, and the reality of a 140 trillion token economy.
Then we moved into the microscopic software optimization.
Right. MOE routing and variable length speculative decoding to aggressively save compute and memory bandwidth.
We explored the complex mathematics of multi-agent orchestration.
And how measuring Shannon entropy can diagnose and prevent catastrophic system degradation.
And finally, we looked at how all of these optimizations culminate in generative physical AI, allowing embodied robots to perceive, map, and act in the chaotic physical world in real time. And as requested by the profile of the data scientists and engineers who listen to this deep dive, I want to leave you with a novel, applied machine learning use case to mull over.
Okay, let's hear the pitch. Tie it all together.
Imagine a unified, highly autonomous application deployed by a national energy grid operator.
I'm listening.
The system continuously runs Microsoft's Aurora 1.5 Earth system model.
Okay.
Using probabilistic ensemble forecasting, it predicts a severe, highly localized weather event, say an extreme ice storm, that is mathematically guaranteed to damage specific high-tension power lines in a remote mountainous area.
Before it even happens.
Right. The moment that probability threshold is crossed, the system immediately uses a multi-agent orchestrator to plan a preemptive response strategy.
And crucially, this orchestrator is continuously mathematically monitored for low entropy dynamics.
Yes, ensuring there are absolutely zero hallucinations, erratic API calls, or logic loops in the deployment strategy.
It has to be deterministic and safe.
Exactly. Once the plan is verified, the orchestrator dispatches a fleet of embodied autonomous drones running the Lingbot VLA 2.0 framework.
Out into the physical storm.
Because these physical drones have strictly limited battery capacity and absolutely cannot rely on cloud latency for collision avoidance in a storm, their onboard processing utilizes highly specialized, custom-developed inference ASICs.
Just like we discussed.
These onboard chips are running SGLang DSpark. By utilizing confidence-driven, variable-length speculative decoding, they minimize the compute overhead and keep the KV cache perfectly clean.
Allowing the drones to process Lingbot Map's 3D spatial reconstruction of the treacherous environment at a flawless 20 frames per second.
They navigate the physical world in real time, identify the downed lines using their MOE visual encoders, and perform highly complex, automated physical grid repairs.
Entirely autonomously.
Before the human population even experiences a prolonged blackout.
Wow.
That specific scenario is the ultimate necessary convergence of macro hardware, inference optimization, multi-agent orchestration, and physical AI.
Here's where it gets really interesting. The foundational pieces for that exact future are already running in the open source repos we talked about today.
The hardware is being fabricated, the math is being proven, and the code is live.
Go build it. Thank you for joining us on this deep dive. We invite you to bring your curiosity back next week as we tear into the next stack of sources.